Okay, today we're going to talk about relative velocity. The first thing we need to talk about is really a frame of reference. A frame of reference is just a set of coordinates that allows for measurement of position, speed, etc. A frame of reference can be you, it could be an object in the distance. It's just a set of coordinates that you're using to kind of measure things with. So we can use a frame of reference to determine the velocity of an object, and we know that the velocity of the object is dependent upon the frame of reference of the observer. So, for example, a person holding an apple in their hand as they drive at 60 kilometers per hour would measure the speed of the apple as 0, right? So I'm driving along and I've got in my hand, for some reason, I'm holding an apple and I'm driving and the car is traveling at 60 kilometers per hour, but I'm just staring at that delicious apple and I'm thinking that apple's not going anywhere. So relative to me, to my frame of reference, the velocity of the apple is 0. But to a person standing on the side of the road, watching this apple move, they're thinking, wow, that's a really fast apple, right? They think the apple is traveling at 60 kilometers per hour. So we can use frames of reference to determine velocities, and we can also then add and subtract velocities with different frames of reference to get the velocity in a particular frame of reference. So for example, person A is walking at 3 kilometers per hour forward relative to a moving walkway. So this vector then would look like this. It would have a start and a point, and normally we would say, okay, that's the person A, that's the walkway W, and this then represents 3 kilometers per hour. The next thing it says person B is walking forward on the ground at 2 kilometers per hour, and the walkway has a speed of 5 kilometers per hour with respect to the ground. So we have another vector that starts walkway with respect to ground, and that's then traveling at 5 kilometers per hour. So a person is walking on the walkway is moving. Obviously, we're just going to really add these vectors together. So the total vector going from A all the way to G, so the velocity of A with respect to the ground is then just the vector sum of these two things. It would be 8 kilometers per hour. So we added those two vectors tip to tail, right? The tip of this vector is the tail of that vector. Notice that the tip and the tail have the same label, which is important when we're adding vectors relative to each other. So in terms of a vector equation, it would look like this. I would say that the velocity of the person A with respect to the ground can be determined by doing this. The velocity of A with respect to W plus the velocity of the walkway with respect to the ground. So we see then that this is our start point. This is our end point. This is then the tip, and that's the tail. So we add these vectors tip to tail. The tip and tail will, in essence, kind of cancel each other out, and you get then a vector that is AG. So the outside two letters are the vector that you're going to get as a result of this. So sometimes this can be a little bit trickier. This next one says, what's the velocity of A with respect to B? So I have to then try to determine what this is. So again, I know the velocity of A with respect to the walkway, and I've also then determined the velocity of A with respect to the ground. So I know that that's 8 kilometers per hour forward. So using this idea of vector addition and this tip to tail idea, if I could find the velocity of the ground relative to B, then I would be able to add it onto here. So to get the velocity of A relative to B, I could take this vector, the velocity of A relative to the ground, and I could add in the velocity of the ground relative to B. Now that sounds a little strange, the velocity of the ground relative to B, but obviously as B is walking forward, the ground in essence is going the other way. So we then say this, that the velocity of B with respect to the ground is the negative of the velocity of the ground with respect to b. So, using these vectors, I can then say, okay, I've got 8 kilometers per hour for the velocity of A with respect to the ground. It told me in the question that B is walking forwards on the ground at 2 kilometers per hour. And so then the velocity of the ground relative to B is going to be negative 2 kilometers per hour. So the velocity of A with respect to B is then equal to 6 kilometers per hour. And if you kind of just think about this in a logical fashion, right? A is walking on the walkway, so they look like they're going super fast. And B is only walking on the ground at 2 kilometers per hour. So in essence then, A is walking or is moving at 6 kilometers per hour more than B is. Right? And that's what this relative velocity is. So as measured by B, A is moving at about 6 kilometers per hour. Measured by the ground, A is moving at about 8 kilometers per hour. And then measured from the walkway, A is moving at 3 kilometers per hour.